We have our yellow outline, right, and then the white set. By the way, I got another handout. It's on the copier. I'll get it at halftime, and that will be the first handout on stereochemistry. I will also send you one by email today that I expect you to print on your own. Okay? We will be starting stereochemistry on Monday. Okay? All right, rearrangements. Carbocation rearrangements. We did the one at the top. Carbocations always prone to rearranging. You gotta know about that. Let's look at the reaction below. You ready? Let's look at this reaction. Looks like we have an alkene and aqueous water. Aqueous water. I mean aqueous acid. It's like a hydration of an alkene. Right here is something good for a note card. I mean maybe a simpler reaction. Note cards, good for showing reactions and then the products on the backside. Looks like alkene. We're getting, okay, hydration of an alkene gives an alcohol. Where we're going to make cation at, because in all the reactions we've covered thus far, the alkene reacts with H+. Either ionically or covalently, it reacts with H+. Same thing here, reacts with the H+. Where are we going to leave cation at, top or bottom? Bottom. Bottom. So we got H+ in water, right? That's what H3O+ is. This attacks like this, these electrons move out like that, and we get boom, 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 boom. New H there and plus here, right? Because the electrons hinge out and go make bond, meaning the lower carbon is without a bond and it's a plus. How do we get to minor? Well, water, yeah, then adds here. These electrons add there to get oxygen bonds there, but we do not lose any H's. Where did I lose an H at here? I did not. It's there. Electrons may bond to carbon. 2 electrons are now bonded to the carbon. That's a plus charge. There's an intermediate. Now we lose proton. Now we don't just magically lose it. We show a mechanism for losing it. Something has to take the proton. What can take it?
Another water molecule.
Well, I'm showing this very generically. There's got to be a minus here. Okay, like a Cl minus, but we don't want to use HCl here. What type of acids would you use here for this reaction? They were listed on the other page. Sulfuric, phosphoric, or HF. Here the anions won't attack the cation. If you use HCl, the Cl could have attacked the cation. You get alkyl chloride. We only want water to attack. Well, you can also use water to remove proton. And if we were, these electrons make bond to H, this is just an acid-base reaction. These electrons move on to oxygen, we get that plus what? H3O plus reform. That's basically acid reform. Acid is the catalyst. But that's only the minor product. How do we get the major product? How do we get the water bonding to the other carbon? Carbocation rearrangement. Last time we had an H slip over here. Well, here instead of an H, there's no H over here. All this is methyls. Methyl, methyl, methyl. Well, the same thing. These electrons start liking the cation. Here, I'm a methyl now instead of an H. You're a cation. The electrons just, sorry, I'm going to move over here and go bond over there, okay? It just happens to be a methyl. So, we take the electrons, you pull them away from this carbon like this and move them over. You do not do something like this. I don't know what that means. Looks like you're trying to say the carbon is moving, the electrons. Aerosolute movement of electrons. When that moves over, what does that give? See, two things can happen here. Water could add, or this could rearrange. To rearrange, we would have what? Only two methyls there. Boom. But now there's another methyl over here. There's a new H there. But which carbon is plus?
That's the one on the left.
The one on the left. Because it lost the bond. Well, why is that not plus? Because there's an undrawn H there. How do we know there's an undrawn H there? Well, it's right there. How many H's here? One. There's one there. There's one there. See, it's got 4 bonds. You got to know where your H's are at, etc. Plus is there. Now, do you see how we get the major product? Now the water adds, these electrons add to the cation. You get your intermediate, I'm not going to redraw it, and then you lose proton, okay? By the way, when I don't redraw something here, it's just because I did it right before. It doesn't mean on the test you just, well, I don't have to redraw it. I assume you're all, okay? I expect you to see that. So do you see how we get the major product? It just came from a rearrangement, but it wasn't a hydride shift. What shifted here? A methyl. But what's a generic name for methyl, ethyl, propyl? What's generic name for like methane and ethane and propane? Those are all alkanes. So what's generic for methyl, ethyl, propyl, which is what you call it when it's in the substituent? Alkyl. I reckon you could say alkyl. But an alkyl group. So this was an alkyl shift. Now you might want to say, well, is it called an alkyde shift? That might make sense, but it's not. It's called just an alkyl shift. What do we have? What type of cation did we originally have? Secondary. It rearranged to what type? Yes. Does that make sense? Rearranged to a more... What if we do a reaction coordinate diagram for this? For giving the major product. Reaction progress, some type of energy, some arbitrary starting point. We're not putting units here. The alkene, I'll call it A, so we don't have to draw structures. A, yeah. First intermediate B, then this is C, this is D. D is going to look like that, except it's going to be bonded there, and then finally A, B, C, D, what's next? E. A is there. Where's B going to be compared to A? It's an ion, yes. No, it's not only is it an ion, the carbon no longer has an octet. So I'm going to put B up here. Okay, where does C go compared to B? Same, higher, or lower? We've already kind of answered that. That's a secondary cation. This is tertiary. Tertiary is what? Lower, right? More stable? I mean, that's why we did the rearrangement. We don't rearrange to a higher energy thing. We rearrange to a lower energy. So, but it's still a cation, so I'm going to maybe do it like here. Then what do we get? D. Well, again, D looks like this. It's just the oxygen's bonded here. Where do you think D is compared to the carbocation? Well, it's actually even lower because in such a species, everything has an octet. I would put D something more like down here. Now, I wish I would have put all this higher. I'm going to move A a little bit lower. Even lower. And then finally E. How could it compare to maybe the starting? What did we do here? Starting has a pi bond. What did we make here? What's new?
Sigma.
2 sigmas. There's your water, H2O. We added water across the pi bond, but we made 2 sigma bonds. Is it to be stronger bonding or weaker bonding?
Stronger.
Stronger bonding. Stronger bonding is lower energy. It should be lower energy, so I'm going to put it on down here for something maybe like this, E. I could have moved it over a little bit. Here's your progress. It goes A, B, C, D, and then E. Okay, how do we get there? Something like this. Now, from here, we're starting to fall downhill. It's not going to take much energy to fall downhill. A little bit of activation energy for each. What looks like the rate determining step? The first step, forming the carbocation, the initial carbocation. That's the more difficult step with the highest activation energy. From there, the activation energy is kind of easy as you fall downhill. Rate determining step is your formation of your initial carbocation. Why did we make cation on secondary current? What if we did the reaction where the cation was on the right or the upper? Make a primary, which we don't get. The primary would look like what? UH here and cation there. We don't get that. We'll give this an F grade because we don't get that cation. But if we had plotted F here, where would we have plotted F compared to B? B is secondary. F is primary. Primary would have been
Higher.
higher. So primary would have been like here. And if the reaction went that way, it starts with the same species, but as it proceeds, it differentiates because it's reacting at a different site. It starts differentiating. It's going to go like this. It needs higher energy to get to F. So, which pathway is the reaction going to take? Is it going to go F or B? It's going to go B. But that's why when I asked you left or right, which way is it going to go, that's what we're asking. It's going to go this way because the energy is easier to get there. Water doesn't run uphill if it doesn't have to. We get B. The reaction is going to be regioselective. Okay? Questions? Making sense? Yeah? Questions? No, no F. The only thing is, how do you get the minor? Depends on how fast this rearranges. Because you could possibly get the water adding to the cation before this rearranges. If so, that gives you your minor product. For us, what do we say? Always rearrange. You say the rearrangement is going to be the major outcome. Ring expansions and contractions. We'll cover everything on... okay, we're under row number 4. Ring expansions, these are just fancy alkyl ships. Look at this reaction here. If you react this alkene, it also has the 4-membered cyclobutane ring with HBr. You can add HBr to the compound. This has HBr added to it. Do formula, it's got HBr added to it. But if you look at it, we went from a 4-member ring to a 5. So that's obviously called a ring expansion. What's the mechanism for this? How did this happen? Well, we start with the same thing. The only reactivity we have here is the pi bond. And we got H plus here. Okay? If you want to do it covalent, you can do it covalently. Where are we going to leave cation, top or bottom?
Bottom.
Cation on the bottom, right? So we want to break away like this and move these away. And that's going to give 4-member ring methyl, boom, boom, boom. Positive here. Okay, you guys are just drawing what I'm drawing. Here's the problem. If I was to sit down with you and say, draw the first step here, as much as half of you would not even be able to draw that right there. Because just drawing what I draw on the board, you're not really testing yourself. You've got to sit down and do it yourself and draw it, okay, instead of just repeating what I draw. And you got to add it. Are there any questions about what we just did there? This is about the 8th time we've done just that initial step. There we go. Now, BR can add here, yeah? But that ain't going to give that product. Our mission is to give a mechanism for forming that product. That's what we're doing here. So how does it form? Well, a carbocation rearrangement. Look, next door, got this bond here. These electrons could just move over. All right? Let's yank them away from that carbon and move them over. Now, these electrons here can move over. Lots of electrons can move over. But if we do that, now I'm going to kind of draw this. The new H is there. Okay? These electrons used to be here. But instead of the bonding there, we're now going to bond them here. All right? And that's supposed to be a straight line. It doesn't matter. Sometimes I will draw bonds like this. But it just moved over like a windshield wiper type kind of thing. But where's the plus charge now? Right here, right? Good. There you go. That's the same thing we did on the previous reaction. It's just connected back here and it's in a ring. What size ring do we have now? That's a 4, but this is a what? 5. Now if you redraw this a little nicer, 5-membered ring. It's a 5-membered ring with 2 methyls next door, but one of them is sitting on a carbocation. So that's that. Now do you see, we're only one step away, right? Yeah? What do we need to do? I mean, the bromine right here gave this plus Br minus, right? Because right there, doesn't that arrow create Br minus? Well, this guy's watching it, you know, it's sitting there watching it rearrange, but then it's like, okay, here I come, you know, bam, and there you go. A ring expansion, just a type of carbocation rearrangement. It's a type of alkyl shift. We went from what? A secondary cation to what? What type of cation did we go to?
Tertiary.
Tertiary, right? We fell downhill in energy. We rearranged to a more stable cation. Not only to a more stable cation, but what do you know about ring sizes? What size rings are best?
Larger. 6.
5 and 6 are best. This has some ring strain. For ninth grade geometry, we see a 90-degree bond angle here. Not 90 degrees C, 90-degree bond angle. That's a tetrahedral carbon. It wants to be 109.5. You want to open the ring up 5 and 6. So we went to a better sized ring also. That's another reason it's a better intermediate. What if instead of this bond kind of shifting here, what if we did a methyl shift here? What would that product look like? Can you draw the product that came from a methyl shift here? See the methyl? What would the product look like if the methyl had shifted instead? Right? I'll use the same structure. I'll change the ink. You may not have different ink, but or just call that A. That's the A pathway. Okay? Or these electrons. Somebody pull the pen over. Okay? I'm going to sort of take this and yank these electrons and move them over there. We'll call that a B pathway. What's that going to give? Well, the 4-member ring has not been done anything to it. Boom. This may end up being a bad bond angle, but we're not really worried about bond angles. We can sort of straighten things up. Boom. There's an undrawn H there on the end, right? But now what else is on that? What else is on this carbon? Another methyl. Now you can call this one the original one and that the new one. Doesn't matter. You got free rotation here. And where's the cation at now? Right there, right? And so if Br minus attack there, you get Br and isopropyl group. Which way is more likely to occur? The A rearrangement or the B?
A.
A, yes. Well, this is a tertiary cation. It went from secondary to tertiary, but which tertiary is better?
5-member ring.
A 5-membered ring, okay? So you would not say that this is going to be your major product. You have rationale for saying that that's going to be your major product. Can this rearrange any other way? What if this bond shifts? Now we would have to sort of turn something, but it may be the same thing. I think there's a question in the workbook about showing multiple different possible rearrangements. Okay. Let's look at the one below. This does not look like a ring expansion. It looks like a what?
Contraction.
Ring contraction. A lot of times you can draw the size of the ring, just say like 7 or 6. Clearly denote that. Maybe you should try this one on your own, and we'll look at it on Monday. Supplies mechanism using appropriate arrows. Please read and reread the mechanism intro I gave you in the beginning of which handout? The yellow one. Yes. Back at the first page. Common mistakes there, discuss. if that mechanism was dry. Okay, yellow sheet. Where are we heading to? Still under A. Carbocation rearrangements, ring expansions, I should have said, and contractions. Ring forming reactions. Look at this reaction. Take this compound, which actually has two alkenes. By the way, if it has two alkenes, you can call it a, wait for it, diene. Okay? Three coming off. If it has three alkenes, triene. Okay, you're getting the hang of it. All right? So, we got this diene here. Reacting with HI, we can get this ring. We can make a ring here. Now, if you look at formulas, yes, HI has been added to the formula. Mechanism for this. Okay. You know what we say where you want to make cation, top or bottom? You have two choices. Well, here you have four choices. But it's the same thing. You're going to make cation typically the best place. Where would you rather make cation at here? Of the four. Well, let's start here. Left or right?
Right.
Here, yeah. And if you made cation there, it would be what type of cation?
Tertiary.
Tertiary, okay. If you made cation here, it would be what? Primary, secondary? Yeah. Tertiary cation. That's going to be the cation that's easiest to form. Now, hopefully you'll be rewarded by going down that pathway. Occasionally you may have a product that's like a minor product when you're asked to show a mechanism, and it would have to come from some other cation. Let's begin with the forming this tertiary. That is, we got H plus, I minus, and the electrons move away. Right, the electrons, right? These electrons attack H plus, and we're going to get boom, boom. You bond to H, that's a cation. Boom, 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 boom. Is that right? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Don't lose track of your carbon. What can attack the cation? Well, the iodine can. And we will have added HI to the molecule, but it won't be that product. So what else can we do? What else can add to the cation?
The pi bond.
We've got this alkene over here. Have you ever seen an alkene attack a positive, a cation?
Yes.
Where?
And all of our other reactions.
Right here.
Yeah.
Did we say it had to be an H plus?
No.
Could it be a C plus?
Yeah.
It can. The alkene attacks the C plus. How? Looks like it's way over there. Yeah, but all this has free rotation. It can all rotate and be right there. So I'm going to sort of redraw this. I can get one of these to write. What if I redraw this? Let's see, I got a cation here, two methyls. One of them has a new H on it. And then I've got boom, 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 boom. Let's see, 1, 2, 3, 4 coming off. 1, 2, 3, 4 coming off. Then the alkene. Now, if we have it like this, because these just rotated, okay, here's double bond. What if this, first off, if this attacks something, where are we going to leave cation here? Top or bottom?
Bottom.
Bottom. So can you imagine this breaking away from the bottom and just hinging up and going to make bond up there? Yeah. Just pull the electrons up and go make bond. Just like this. Pull my pen. Pull it up and go make bond. And that's what the arrow means. And that gives what? Which carbon is bonding to the upper carbon?
The top one.
The top one. You see? A lot of students say, it looks like you said the lower carbon is bonding.
That would just rotate like
No, because the arrow is not showing movement of atoms. I'm pulling the electrons away from that carbon. Here's the lower carbon. And I'm going to bond to the top one. Okay? The pin is still bonded here. We broke away from down there. That's the type of thing you got to understand with the arrow movement. What size ring we're getting? This is now bonded here. 1, 2, 3, 4, 5, 6-membered ring. Now we can draw a 6-membered ring. This upper carbon has 2 methyls. Yes, one of them does have a new H. Which bond did we just make here?
The top one? Or
Yeah, right there. I like to highlight the bond we just made sometimes. We just made that bond. I mean, here's the pin. Now it's up here. Pin is that bond there. I sort of messed up by not making this little. If I drawn I should have drawn this like this. Or really, over there, it should have been drawn like that. Swing it up. Where's the cation at? Cation is actually here. Because look, if I had drawn it like this, don't erase. If I had drawn it like that, that would have been a more appropriate drawing. Then this just hinges up. This hinges up. These electrons are now bonded here, but it broke away from that carbon. Now you'll have to just go with me here. That looks like it's not bonded to anything, right? That's just me drawing. If I take time to draw like that, they're actually going to look ugly, but sometimes they don't. So sometimes they're not connected. Right? That's starting to look ugly up there. I'm going to get rid of that draw. There we go. Huh. Now look at product. What do we need to do to get the product?
bring the iodine down.
Yeah, the iodine's been watching. Now it gets a little excited and it's like, okay, I'm going to do something. Bam. And there you go.
In our reactions, can we bring the iodine straight from where we wrote it to begin with, or do we need to redraw it right next to it?
You can. I mean, I almost did this. You know. Bam.
So that's fine.
I just wanted to save the ink, so I redrew it. The flask is usually about this big. It's in there. Okay, yeah? Please see the consistencies. We're building okay, as we go along, we add more and more. You develop a rational thinking process, ability to show mechanisms using arrows correctly. There you go. So there we did, what did we do? We made a ring, so it's a ring forming reaction, but what do you call it when something like internally reacts? The internal alkene is a reaction internally, not intermolecular, but intra. An intramolecular reaction of the alkene with the carbocation. Yes, alkenes can attack carbocations. Okay, down below. Polymerization. By the way, before we get off of ring forming and get to polymerization, let's try a little THC. be variations of ring-forming reaction. Maybe instead of the alkene doing the reacting, maybe the nucleophile does the ring-forming part. I don't know. Please look at this. But look, no ring, now ring. 6-membered ring formed here in the THC. Think about this if you haven't already, but now you're ready to think about that. Show a mechanism for that reaction. You know, the cannabis plant makes these molecules. That's just amazing, you know? Largely from like CO2. I mean, there's a lot of work that went into making just this. But then the last step is right here. The plant, you ever heard of MacGyver?
Yeah.
Okay, I don't know how you guys did, but I grew up watching MacGyver making bombs from rubber bands and paper clips and stuff. Can you imagine the plant making that from the CO2? That's like MacGyver stuff. CO2 and water, and I can make that big molecule. I mean, yeah. But guess what? There's mechanisms. There's for each step. Maybe a little fertilizer in there too. I mean, there's supply some other things. Some nitrogen. Compound doesn't have nitrogen. No nitrogen in THC. How about that? Okay, let's look back over here at the idea of cationic polymerization. If you take this simple alkene, what's the name of that simple alkene? Watch the nomenclature video.
Vinyl or vinyl something?
Longest continuous chain is 3, so that's it's an alkene, so it's propene. Positions of alkene in.
1, 2.
You watch the video?
It's 1, 2, right? 1, 2.
Okay. I'm not going to watch the video before the test. Test is what? Monday week. Yeah? What? Monday week?
Never.
You just did. Monday week? That means not this month.
Yeah. I got it now. You'll see it. You said Monday. I said,
All right, if we take propene with an old H+ catalyst, we can polymerize it and get a polymer. Now, slang name for propene is propylene. And if you polymerize propylene, you get polypropylene. And some of your water bottles may have a PP on the bottle, which stands for polypropylene. Polypropylene tends to be kind of a cheap plastic, a thin plastic. Okay, let's look at this. What's a polymer? A polymer is where the original monomer just reacts over and over and over and over, and you have multiple units. And the polymer consists of multiple units of a monomer. And we can show the monomer sort of in brackets with an N. And N is some huge number of repeating units, like 100 gazillion. And it's called a polymer. But polymers take on very different properties than the original monomer. This is probably a very low boiling liquid. Polymer is a plastic, it's a solid. Now there's also some material science in there that turns the outcome into more of the plastic and can shape it and stuff. But we're getting into materials. Polymers are used for materials. Your headlight on your car, it's not glass. It hasn't been glass since like the 1950s and 60s. It's plastic, but it's usually a very nice plastic. It's thicker, it's more transparent, and those could be some higher end polymers. We'll see a variety of polymers as we go along, a different polymer type of forming reactions. This is called a cation polymerization. This referring to it's initiated by a cation. Where's the cation? Right there. The cation initiates the reaction. Okay? How do we get there? Well, there's not a lot new here to begin. This H+. This is going to react. Where are we going to leave cation? Left or right?
Left.
Correct. So this breaks away here, and we get boom, boom. New H here, right? Cation here. Okay, what can attack here? Well, is there any minus here? Note that I'm not using HBr. Because if I did, Br could attack here and we would just have a monomer outcome. Well, I'm not telling you what to use here. Because you can't just have H+, you got to have the minus also. So what acid, we don't want any well, maybe I'm ahead of myself. Let's first see what attacks here. What attacks the cation?
Another polymer?
Another propylene or propene. Just like above, except this time it's intermolecular. Let's put the alkene here with the methyl. There's another propene. It's going to attack this, just like if it was H+. This is going to bond here. Tell me this, which carbon is going to bond here? The left or right?
Right? No, it's left.
The left carbon will. Why? Because we want to leave the right carbon as what? Carbocation. Same thing here. Anytime your alkene reacts, where are you going to leave the cation? So I'm going to pull away from here and get this. What does this give? Well, you got to kind of make sure everything's right. Boom, boom. There's a new H. It rotated. Okay, here's that. Made a bond. But this is what? Boom, boom. With cation here. Now, I like to indicate we just made this bond. These electrons moved over and made the bond. See, that was the original double bond here, right? They moved over and made a bond, leaving that carbon as a plus. Well, what can attack that plus?
Another one.
Another one. So let's draw another one. And when this attacks, which carbon is going to bond here? Left or right? Left. Because that will leave the cation where we want to leave it. So this hinges up like this. What does that give? Boom, 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 boom. I'm going to kind of draw it a little straighter on the board now. There's what got attacked, so we made a bond to it. Boom, boom. And the cation is here. We made that bond. There's your propene. The electrons broke away from the middle carbon when it made bond, leaving the middle carbon positive. Why are we leaving the middle carbon positive? Why did we leave the middle carbon positive? And not an end carbon? Because it's secondary. The end carbon would be primary. Well, what can attack this? Tell me when to stop. A gazillion times. And before you know it, you have one long, huge molecule we call a polymer. Okay? How do we draw this? Well, you draw it by just drawing the repeating unit with an N. I've got it drawn up there, but let's draw it from scratch. First off, what do we have here in terms of repeating? There's an H on the end, which is sort of new. That started everything. But from there, we have a CH2 carbon methyl. CH2 carbon methyl. CH2 carbon methyl. The repeating unit is the what? CH2 carbon methyl. What do I have inside my brackets? CH2 carbon methyl. CH2. This is just a long thing, and I just kind of cut it off at some point. Okay. But an H started it. Now I could have just shown this as, that's it. Okay? I could have just shown that, and that with the end there, and that would have been enough to show you the polymer structure. With the H maybe sometimes shown as well. How are we doing? Questions here? The alkene just attacks over and over. What type of acid would you recommend here? HBr or H2SO4? Why? Because we know the anion of that won't attack anything. If you had used HBr, boom, Br would attack cation. You never would have got your polymerization. So choice of acid would be important. How does this thing end? For us, we'd probably leave it kind of undefined. There's a variety of ways the polymer can end. It doesn't just go on for infinity. There could be traces of water around, and water attacks cation, and your end is just like OH. Okay. There's other ways it can end. For us, this is sort of all we're going to do, be able to show the outcome, and be able to show a repeating unit. Okay, let's see where we're at on the yellow. Summary scheme here. We've done all the top down. We've done that for a while, and we showed you miscellaneous stuff. If you haven't recognized it yet, all the reactions we've done at the top all involve a carbocation intermediate. They all involve reacting with H plus as the electrophile. Certainly initially. In the polymerization, we do it initially, but then we start reacting with the carbocation as the electrophile. Okay, now we're ready to move down to some a little bit more complex reactions. Reactions involving other electrophiles, other than H plus. Now, these do not involve a carbocation intermediate. They will not involve a carbocation intermediate. Because of that, we can make this statement. They're not prone to rearrangements. You only get rearrangements with carbocations. Here are the reactions down here. We will start here with X2. This is like Br2, elemental bromine, Cl2, elemental chlorine. Okay? And then we'll come around this way, I think, although it may not be in that order. Maybe close to that order. Then we'll move down to the bottom with the hydrogenation. Before we do that, though, let's take a 2-minute break. Stretch your legs.
Do you guys remember if you went through this? You did, yeah. I don't understand. Did you do the one on the back with iodine included? Yeah, this one. So if you replace iodine, if you put iodine into it instead of the chlorine, It was endothermic. The values of iodine for the bond made it endothermic versus exothermic with the fluorine. And then if you do this on the front, you did this, right? Did you get, what did you get for your iodine reaction? It's the thermodynamic, it's like 10. What was your value for this one down here? Yeah.
Well, no, we didn't, I'm gonna do that.
Yeah, so for the bonds for this, I thought it was, yeah, 6 of these, and then it was 3 of these, right? 3 iodine. So that, maybe I did my math wrong. No, I got, it was different. I got 564 down here. Used these values.
So you did the
Yes, I'm gonna, I don't know, let's. Yeah, so the first one should have been, yeah, it was like 1,015. Oh, no, you're talking about, oh, the N2, so this is,
Like, obviously,
the
it's like,
two
oh, I didn't
that was
calculate
two,
that.
but I think it's just one. So this one, 945, 43.
So this is 945. Okay, cool. So your total value for the bottom was what? 381, and then for the top? Okay, so then that makes sense. So 381, if we go back to here. Because I did my math wrong up here, I was really confused because I was like, it was like they flip-flopped, the trend wasn't the same. So that makes sense. But I don't really understand why the iodine, I guess it's like the size of the atom that changes.
Yeah.
So it's either, so if this is, that means these bonds.
Blue handout going around.
Then
One blue handout.
fluorine.
This is the outline for the stereochemistry, which we will likely start on Monday. I don't typically do averages. It's pretty average.
Sorry.
Okay. Anti-trans addition of X to the alkenes. What does anti-trans mean? Let's make sure you know. Typically, the X2 is either chlorine or bromine. Iodine, I2, doesn't react well in these reactions, although you can do some modified reactions with iodine. F2 is quite dangerous. The reason iodine doesn't react is because it's very sluggish to react. By the way, we did not go back and look at the thermodynamic calculations. Okay, we'll need to do that on Monday. Please do thermodynamic calculations. We'll see what type of questions you have on that, including those on the first page. Fluorine, on the other hand, is too reactive. Carbon-fluorine bonds are very strong, and so the reactions are very exothermic. So exothermic that often you can get some explosions. F2 can be dangerous. fluorine chemist. It used to be at Clemson. Yeah. Who lost an arm, half of an arm, and a couple of fingers on the other, doing fluorine chemistry. He's now retired, although he may still be around the chemistry department. That happened when he was in graduate school. I was fortunate enough to have lunch with him one day. Okay, chlorine. So we're not reacting with H+. Is chlorine electrophilic? Does chlorine have any partial positive, or it certainly doesn't have a full positive, any partial positive? Well, it looks like it's purely nonpolar. But your halogens are known to be polarizable, even though they don't look like it. That is, they can be just sort of stubborn and fight with each other. And you can get a temporary polarity here, even though it doesn't look like it from electronegativity. It looks like it should be a plain nonpolar. Because of that, one can temporarily become partial positive, then the alkene can react and kick it off. A lot like you would be doing like this with HCl. But HCl is certainly polar. Okay? So we're just really replacing the H with another chlorine here, another halogen. Where are we going to leave cation at, left or right?
Left.
On the left. Correct? So this is going to bond to chlorine and leave cation on the left. Have we ever did anything differently with that question? The answer is always the same, right? See the consistency? Okay. If we get cation, how can we get final product? Now the outcome is an addition of the chlorine across the pi bond, that is to each carbon of the pi bond. And so now we have a chlorine here and here. And you can draw them in any direction, because right now we're not worried about stereochemistry. Just connectivity. Here and here, which was originally the alkene carbons. We added chlorine to the alkene. Mechanistically, we could get that by the other chlorine, from there, the chloride, adding here. And A would give that outcome. Would it not? It would. It would give the outcome. Problem is that's not the mechanism. Not the mechanism. Let me ask you this. Which chlorine lone pairs are closer to the cation? The one that's bonded here or the one that's not bonded? Which one's closer?
Bonded one.
One that's bonded. Because this guy, like you said earlier, could have been way over there. Remember how we had to go way over there? But guess what? This guy's right next door. These electrons are going to be faster to add to the cation. Aren't electrons attracted to positives? That's physics. This is what happens. This guy comes in, and I'm going to call that back bonding. Now, most books don't call it back bonding. So I'm going to call it back bonding. What does this lead to? It leads to this, because if you make a bond there, there's your bond. That's what it leads to. Well, this is a three-membered ring. It looks strange. It is. But it can form. And the chlorine here is positive, lo and behold. You can do a charge. Some of you can. Graded the test. Some of you need to work on how to determine charges. That's a positive charge. And there we go. Now, some of you may be wondering, but I thought you said these reactions don't involve carbocations, right? Did we say that on the summary page? I knew you were thinking that. So why am I showing a carbocation? That's because it's not actually formed. Not actually formed. Okay? Most books will not show this. I show it because I think it helps. What's really going on here? These two steps actually happen at the same exact time. That is, as soon as this is attacking, these electrons are coming in here back bonding. But to me, if I start doing all this, you guys just glaze over and can't see it. So what we have here is a concerted two-step process that happens at the same exact time. I'm showing the two steps separate, but I'm telling you that they actually happen at the same time, and because this actually never forms. And most boats will go directly from here to there. This is not actually formed. I think it's useful to show it there. It's going to help us down the road in other ways. Okay, it will help us. All right? Now, how do we get to the final product? It comes from this. This is called a chloronium ion, by the way. If it was bromine, it would be called a bromonium ion. You could also get an iodine, you get an iodonium iodine. Okay. Here, the chlorine attacks this carbon. This is a new type of attack. We're not attacking a carbocation. We're attacking an atom and kicking another one off. Here we call this a leaving group. Okay? Where is this discussed? I don't know. It may be discussed on the back of the first page of the yellow. It's the second general mechanism type. The first type was attacking carbocations. The second type is attacking a carbon and kicking something else off. That's what we're doing here. This makes bond here. These are like, what does this arrow mean to you? The electrons are breaking away from this carbon, moving on to that chlorine as a third lone pair. What does this arrow movement give? It gives that. There's your bond formed by this arrow. 3 lone pairs remaining, because one is now bonded. And then this breaks away, and it takes on 3 lone pairs. And there's your product. This here is a concerted process. This is coming in and kicking off a so-called leaving group. This is actually your only intermediate. If you understand and believe me that this is not actually formed. If it ain't formed, how can it be an intermediate? I'm just drawing this on the board because I think it helps you understand the process. It will help us later. If you draw this on a test, you need to write NAF. Thus, if you were to do a reaction coordinate diagram here, how many intermediates would you have on your reaction coordinate diagram? 1. That good. Everybody with me? Okay. Now, this is called backside attack. Probably discussed on the yellow, because when you do this, when you kick something off, you come in opposite that. Okay? For example, if this is bonded here, it's projected this way, which way are you going to come in to kick that thing off? Oh, backside. You kick it off. That's backside attack. Now, I'm bonded over here. You make your bond. You're bonded on the opposite side. Why? Because you came in backside. That's why. That'll be more important when we start looking at stereochemistry. Right now, we're not looking at stereochemistry. But it's called backside attack. It's opposite side attack, but we never say opposite. We say backside. Okay? Question, why does it attack here? Why would it attack there at all? That's not a carbocation. Why would it attack here at all? Is this bond polar? Cl to carbon.
Yes.
Can we draw a dipole, what, toward the chlorine?
Yes.
Chlorine's pulling. So what type of partial is on this carbon?
Positive.
Chlorine's pulling electrons. You make the partial positive. Okay, but that's a positive. Let's just focus over here. Let me ask you, which pulls more? A neutral chlorine or a positive chlorine? A positive chlorine is really mad. It's like, I need some electrons fast. You've got an electronegative atom being positive. It's pulling a lot here. So that's a lot of partial positive. Okay? So it's not attacking a carbocation, but it is attacking a partial positive, because anytime we react, we're going to have dipoles to consider. Positives are reacting with negatives. But it's not a cation. How do we know it's not a cation? We'll prove that on the next page. Now, some books will show that this is sort of partially breaking. It's a weak bond. They'll kind of show something like this. Basically, what we have here is sort of an intermediate bonding. I mean, this is going to be attracted over here. How much is it attracted? Is it a covalent bond, or is it fully not? Well, you can have in between. You can have a polarized covalent bond. That's what you have here. Let me ask you this. Could we not have done it on the other side? You also have polarity over here. So are they both partial positive? I mean, you can also pull from that carbon. Which one is more partial positive?
The one on the left.
Why the one on the left? This might be a little counterintuitive, so I have to give you the answer. I'll ask you like this. Which can take on more positive? It's the same as over here. Which of these carbons can take on more positive? Well, on the left. That's why we make cation there. Why did we make cation there? Because it's tertiary. But why? Because it had donators that sort of stabilized it. So the answer is this carbon can take on more positive. Same question here. Which can take on more positive? This one. Because it has rich friends donating electrons, this carbon's like, okay, chlorine, go ahead and sort of start stealing the bond. And I'll become a little positive because I got some rich friends donating for me. And so that's more positive. But guess what? It's the same answer as here. It's just, you don't attack a free carbocation. You don't attack a free carbocation. You attack something, and you have to kick off the leaving group. Okay. So it may have looked like a simple addition of chlorine by the A group, but that's not the mechanism. How do we know it's not the mechanism? We'll prove it on the next page. Now, predict the product. This is one of the easiest you'll ever predict. Do the first reaction. You don't have to show mechanism. Just predict the product. Now, I'll tell you, and others will say, you can't memorize an organic chemistry. Well, sure you can. You can memorize a little bit. But then you have to have the understanding and the mechanistic knowledge to go with it. An alkene reacts with bromine to give what? What's the outcome? It's written at the top. It adds to the alkene. It's going to be a trans addition. We'll talk about that. What did we get here? I said it. Halogen on each carbon of the alkene. Right? Okay. Boom, boom, boom. The alkene used to be here, but let's put a bromine on each, and there you go. That's what we did. Now the mechanism is a little bit involved, but that was the outcome in terms of predicted product. Later on, we may have stereochemistry. For example, that is a chiral carbon. I'll star that. We'll have to look at that a little bit later. This one is not. What about the one below? ICL. This is called an interhalogen, where two different halogens are bonded. That's possible. Doesn't have to always be the same two halogens bonded. You were saying what?
It's the same setup here, but eyes down.
You mean iodine on the second carbon?
Yes.
Why iodine there?
Because the partial negative is going to go on the chlorine. That's more electronegative.
Okay, so this has a permanent dipole towards this, so the iodine is partial plus.
Yes.
That's partial negative. Yeah. See, here it's not as easy because here you just put a bromine on each. Here, does the iodine go on the outer carbon or the one or the two? Because you can have two different. Okay. Well, let's work our way through this. The alkene attacks the positive. So this is like HCl. The iodine is electrophilic. So the alkene attacks the iodine. Where are we going to leave cation?
On the second.
In the secondary carbon. So this attacks like this, kicks the chlorine off. What do we get? Boom, boom, boom. So the iodine is out here. And what is this? Well, yes, eventually it's going to be the chlorine, but let's go through the mechanism. Right? Because we understand the polarization of our reagent. This attacks the partial positive, the electrophilic part. Iodine here. Mechanistically, is this actually formed, or what happens?
No, it's not.
Which electrons can attack this quicker? The Cl minus, which is way over here maybe? Or iodine? Iodine, this is going to back bond. And by the way, we know in these reactions that they don't have a carbocation. So this should be NAF. Back bonding. The back bonding gives what? Boom, boom, boom. The iodine is now bonded here. Two lone pairs left. That's a positive charge. See again, as soon as this is attacking the iodine is back bonded. And you never get the cation. I'm only showing it on the board because I think it helps us along the way. But in real chemistry life, the cation is never there. Question?
Did that make a triangle or a triangle?
Three-membered ring? Three-membered ring? Yeah. Three-membered ring with the that's called an iodonium ion. It's strange. It's a three-membered ring. We made it form. Why would it want to form? Why would that want to form over this? Why does the three-membered ring want to form over this? Why would it just stay like this? I tell you, because bonding is a good thing. It bonded. Now, everything has an octet, even the iodine. We have an additional bond. That's why it did it. Yes, it is ring strained. That's the negative thing about it. It bonded. But guess what? The iodine, even though it's bonded, it still pulls. It pulls on, there's a dipole here. Which carbon is it going to be able to pull more on? And which carbon takes on more partial plus?
The tertiary?
This one. It's the same answer as this. And so what happens here? The chlorine, how does it come in here?
That bond.
Well, I call the internal back bonding. This comes in backside attack. Backside attack. Kick off the iodine from that carbon. These electrons move on to the iodine, back to where the iodine wanted those electrons, yeah? What does that give? I mean, we could draw it just like it's sort of drawn. Boom, boom. The bond angle is going to be kind of ugly though. Chlorine here, and then carbon iodine. right? These electrons used to be bonded here, but instead the chlorine came in and kicked them off. That's just ugly bond angle. I've got it drawn, but I don't have it drawn. I would just tend to want to clean it up and give a nice backbone. Here's my original. So chlorine is here, iodine is here. I mean, just a nice, more of a zigzag backbone, which is more perfect to bond angles. So the answer is the iodine's on the N carbon. Yep. Not because we understand mechanism and reactivity. That's an example of the interhalogen. Okay, we already said that below. What's the anti-trans addition? And how do we know it does not involve a carbocation? It's because of reactions like this. If you take a cyclohexene and react it with chlorine, you will end up with a chlorine on each carbon. The chlorine will add across the pi bond. Yeah? But the chlorines will only be trans. They will not be cis. Now, next week we'll learn that this has an enantiomer. You do not get cis. Any mechanism must also explain stereochemical outcomes. Why only trans? Well, let's look down here and compare two different pathways. This can attack, by the way, you can leave cation on top or bottom. Everybody get enough sleep last night? No?
I think top.
No?
Oh, it says it right there.
I'd recommend getting more sleep at home. Okay, pi bond, top or bottom. We're going to make cation on top or bottom.
Top.
Either. There's no reason for it. It's symmetrical alkene. Both. Okay. I made it on top. I could have easily just made it on bottom. Okay.
So there's no like tertiary or secondary, tertiary reason. It doesn't matter.
They'd both be secondary.
Okay.
So there's going to be no regio selectivity.
Okay.
We hit on that before.
Yeah.
But that's why I just made it on. I could have made it on bottom. Okay. Well, let's look at this. This makes bond to chlorine, kicks it off. Bond to chlorine, cation. Is that really formed? Well, no. Let's assume it was. I'm going to show you why. How do we know it's not formed? If it was formed, we should get this. Why is this bolded? Well, look at this. This carbon is now sp3. There's one H there, right? There's still one H there. And so it's tetrahedral. 2 in the plane, 1 forward, 1 back. The chlorine has got to be either bolded or dashed. I chose to draw it bolded here, but I could have also drawn it dashed. And you can get both, and we'll talk more about this as we go forward. Okay. Now, if this was a cation, the next step would be just this attacking the cation. Now, here's something important. When you attack a cation, here we go. Let's repeat over here. There we go. Here's a big cation. First off, ignore the cation. If I've got a leaving group, which side do you attack?
Back.
Oh, back side. Do you attack from the front? You do not. So only one side, back side. Okay. If you have a cation, which side do you attack? Now, it's over here too. There's the cation. Which side do you attack? You can attack either. You can attack over here or here. Okay? That is, the cation. By the way, what's the geometry of the cation here? How many H's here? One. What's the geometry of the cation carbon? It's got 3 regions around it. sp2, trigonal, planar. Planar like a piece of paper. Or the board. Here it is. I'll just move the board out a little bit. You can either attack from the front, and if you did, your new bond would be bolded. Or you could attack from the back. And if you did, your bond would be dashed. Okay? That is, you could either have a bolded or dashed. This is reviewed on the blue thing, I think. Okay, I'll give you some. Right? So if there was a cation, you should get both of these. But this is wrong because we know you only get what? Trans. That mechanism should give cis. But we know in the lab you don't get cis. Same thing over here. If this had originally been dashed, you attack either side, you could get dashed with bold or dashed with dash. Well, again, these are not formed. The mechanism of the cation does not hold up to experimental evidence. Well, we know that there's not actually a cation. That's initial proof. Instead, we have a different mechanism. It's written down there but not shown. Let's show it instead. We know that this doesn't just add here. What happens instead? This back bonds. And this is not actually formed. And if it back bonds, what do we get? Well, this chlorine is forward. When it back bonds, it's still going to be forward. It's going to be like this. Because if the chlorine is forward and it back bonds, I mean, the new bond is going to be forward also. It's going to give that. So this goes directly here. Now, see again, I would rather you go that way, because to go directly here, you got to make another bond, and this gets complicated for you guys, I think. Do it stepwise. Just write NAF. This is the intermediate. Okay. Now, we got to get another chlorine bonded here or there. It's symmetrical. I'm going to bring it in from the top. This attacks here, cause partial plus, and it's pulling. But how does it attack here? Both sides?
From behind.
Or only from behind? Now, if the chlorine is forward, how does the other, if that chlorine is forward, how does this one come in?
Dash.
Back. Now, I'm not going to show with the arrow, but I will show it with my outcome. It kicks this off, and this gives which structure on the board?
The second one.
Yes. Only that, does it give this?
No.
No, it does not. This mechanism fits the experimental outcome. So this mechanistic theory is what is held up. By the way, some of these have actually been isolated. They're very hard to isolate because they're very reactive, but some have, and that's been further proving that your bromonium, chloronium is your intermediate. Not the cation. Here's stereochemical evidence. Over here, same thing. If this back bonded, you would get both chlorine bonds back. Then when this chlorine came in, if this bond is back, how does the chlorine come in?
Front.
Opposite, which is
Front.
forward. So it's really coming in forward, kicking that off. Okay, this is really plain. This is going back, and so this is coming forward, but I'm all in one plane, and that gives what? Well, that's now forward because that's the way it came in. But when that gets kicked off, this is just like this. And there's your outcome. And is it cis or trans? Trans. That's all you get. Trans can also be called anti. And so this is why at the very top it says what type of addition? Anti or trans addition. This is your outcome. There's a reference to where a bromonium ion was actually isolated. Questions about that? Yellow sheet. Let's see if we covered everything for that. Anti-trans addition. I don't think we said vicinal dihalide anywhere. What's vicinal dihalide? Well, dihalide has two halogens, right? We made products with two halogens. What does vicinal mean? So dihalide, a dihalogen, dichloride. What's vicinal? Vicinal is like vicinity. Chlorines are in the same vicinity. Ultimately, that means they're next door to each other. 1, 2. Another type would be if we have maybe the chlorines on the same. That's not called vicinal. Those are like twins. That's called a geminal dihalide. A geminite. Okay? We're making vicinal dihalide. The Belmont horse race tomorrow, or is that next week? Nobody watches horse races? Watch the what? Kentucky Derby?
that.
Kentucky Derby? All right, formation of trans halohydrins. Okay, if we do the same reaction but include water, we get a product like this. We've got an OH and a halogen, not two halogens. This is called a halohydrin. Halo referring to the halogen, hydrin sort of like hydrate or water, and with the OH there. Okay, it will be trans whenever we have stereochemistry. This example does not include stereochemistry. Now, this reaction is regioselective. That is, the OH ends up on the tertiary carbon, not out here on the end primary carbon. So the reaction is regioselective. Let's look at the reaction. Alkenes don't react with pure water, but chlorine can be electrophilic whenever it gets sort of schizophrenic in these dipoles. Halogens are polarizable, right? This attacks the chlorine, kicks it off. By the way, chlorine is never ionic. With HCl, we showed it ionic sometimes. Your halogens are never ionic. They're always covalent. What does that give? Boom, boom, boom. Where are we going to make cation? Left or right? On the left. I think you prefer me doing it like this as opposed to doing all this here. I tried to establish a process. Yes, chlorine here, cation here. Now let me ask you, is this actually formed, do you think?
No.
How do you know it's not?
Because the electrons for the cation.
What's a more general reason you know this is probably not actually formed? Here it is.
Trans.
Here it is. If the new thing has some electrons,
A cation.
the electrons of the new thing are going to be attracted. Okay? If this had attacked, if that was an H, we did yesterday, 2 days ago, can an H back bond?
No.
It doesn't have a lone pair. But the halogen does, and it will back bond. And guess what? It back bonds at the same time that's happening, that all happens at the same time. And we ultimately, the first thing we get is what? That's truly the first intermediate. NAF, back bonding. Okay, now Cl minus is here, it could attack. But if you have water around, it will preferentially attack, even though it's neutral. This is hydrogen bonding, and usually when you do this, usually a lot of times you use excess water. XS, you ever seen XS? Okay. That stands for excess. Instead of chloride attacking, water attacks. Where are we going to attack, left or right?
Left.
It's the same before. Which carbon can take on more positive plus and allow the chlorine to pull? This one, because it has rich friends. The answer is the same as here. The water is going to attack here, but it's not a cation. It has to do it backside. So the H2O comes in here, kicks that off. And what does that give? Boom, 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 boom. Chlorine. What's bonded here? The oxygen. We haven't lost any H's. That's a positive charge. How do we go neutral? What do we need to do to go neutral? Somebody suggest something.
Another,
Another water.
yeah, another
What can
water.
take the
The
H?
CL sitting up there.
Well, you could actually be either of those. I'll do it first with the Cl minus. If this takes the H, leaves the electrons behind, that's just an acid-base reaction, what do we get? This plus what? What did we form here as a second byproduct? HCl. So you get your halohydrin plus HCl. Somebody said water. Well, yeah, we got HCl in water. But this is probably excess. How does HCl exist in water? If you got HCl in water, how does this actually exist?
Ion.
H and CL.
It actually exists like this. Yes. And you could have got there directly by, instead of using Cl minus, we could have used water to take the H, and that would have given you that directly. And that's actually more appropriate. So the person that said water, yeah. But again, I like to use the exact conjugate base, so I reform sort of a specific thing, reform the specific acid. But we know these strong acids in water are ionized. So, do you see why the OH is on this carbon? It all comes from right here. And that came from the previous discussion. But you're really attacking the same place. It's just not a free carbocation. You're attacking this back-bonded thing backside. Not actually formed. Everybody with me? Okay. Repeating the ideas.
So the fact that the OH is left on the bottom when in the product is on the top, it's
In those products, you have complete free rotation.
okay.
I could have drawn the chlorine down or up. It's just like I could have drawn it either way.
Okay.
Once we get to where you have to do it precisely, we'll talk about it.
Okay.
Okay. New term. This reaction is also stereoselective. I could have used this term when we were talking about the two different bromination outcomes. We didn't use it over there. Stereoselective. take this alkene, react with bromine and water. Okay, right here. What type of product you make? An alkene with halogen and water. What type of product? Halohydrin, yeah. That's something good for a note card. Right there is your starting point, that's memorization. Okay? That gets you going. But then your mechanism for your halohydrin comes in, and that's where you can't just memorize, you have to have your understanding. Because if you try to memorize every mechanism, it's foolish. Develop your understanding and see the similarities. But yeah, halohydrin. There'll be, as you go along through organic 2, there'll be lots of reactions where you just have to say, hey, yeah, that's going to be an acetal product. Or yeah, that's going to be a imine. That's your starting point. Halohydrin. But it turns out that the bromine and the OH are always going to be trans. We should know why. The bromine and the methyl will be cis in this example. That is, we're not going to get anything that has maybe the OH and the Br cis. We're not going to get that. What's the relationship between this and this? Are they constitutional isomers or stereoisomers? They have the same exact name. They're connected the same. In both cases, the OH is connected here, the bromine's there. OH here, bromine here. Same connectivity. They only differ in their projections. They're stereoisomers. But you only get one stereoisomer. That's why we say it's stereoselective. Now, next week, we'll also be able to say it's diastereoselective. This is a specific type of stereoisomer, once we learn that. Because these are actually also known as diastereomers. And you only get this diastereomer, so it's diastereoselective. That's a little bit down the road. Supply mechanism for this on your own. Prove to yourself that this is the outcome. You may end up with everything switched here. That means this may be bold dash bold. If you do, that's okay, because that will be the enantiomer. And a lot of this will not make sense until we do stereochemistry, and then when you look back, this information will already be there. How are we doing? Let's see what we can do to finish up. Please supply mechanism there. Think about the stereochemistry. Also predict products down below. Got it kind of cut off there. At the bottom, that's deuterium. Deuterium. Then we'll be moving on to other reactions, including oxides. Of course, yellow sheet. What are we doing so far on the yellow sheet? Finished on halides. We're doing halohydrins now. We'll move around. Epoxides, cyclopropanes. These reactions will all have consistencies. All have consistencies. They'll have their each unique nucleon. We're good with everything. What? Unknown lab report is Wednesday, Thursday. Monday, Tuesday is a recrystallization of unknown. You don't have to prove what the unknown is. But you do collect melting point. I'm not sure if you have to look up the melting point. Slide finder is very useful information. Please watch the video for the recrystallization. Lab on Monday, Tuesday. We're good? Everything? Anything we're missing? Don't let this weekend go by. You are running, okay, it's a 5-week course. Okay, you got to keep on it. Can't let a weekend go by without making good progress. Have a good Friday, guys.